Hi, I'm Randall Hayman, a university mathematics academic. Because of the coronavirus outbreak, I'm using my YouTube channel to make quick turnaround videos on mathematical problems and concepts. So if you're a lecturer, tutor, high school or primary school teacher, a parent, or even a grandparent or a student, and you'd like me to make a video for you or your students, then use the comment section below the video or email me at coronahelpmathematics@gmail.com. Okay. So I'm doing some 4 examples now, 4 or 5, of ideals. Some of you who have followed the channel closely will realise that I've redone this video to make it now consistent with this definition. So this definition for an ideal I'll use throughout. Okay, so let's go, let's get going on this. Example 1. We saw before that 7z was, so let's do another one, 2z. So let's do this. The ring equals the integers, and the ideal is 2z, which is equal to the set of even integers. The integers that are divisible by 2. Call it what you want. Okay, so that's pretty good. That's an ideal. Let me give you something that's not an ideal. Set of odd integers. So that's not. Okay, so that is not an ideal. Why is that? Why is that? Well, if you look up here at that last condition, this is saying if we start here, if A is an odd number, say, because it's in this, what we're testing out to see if it's an ideal, well, let's say 3. And let's say this is now the integers. So let's go 3 by 6. That's 18. But 18 is not an ideal. Not in the ideal. So what I'm saying is A here, A times R is not an element of I. And so because of that, it cannot be seen to be an ideal. Okay. Someone asked me to do something on the ring of polynomials, which I'm happy to do. Let's just fix this up. Okay, let's go with example 3. Here the ring is going to be the ring of polynomials with real coefficients. And here is something that's an ideal. It's not the only ideal of this ring, but it's one of them. F. So this is actually P for polynomial. Let's do P for polynomial. So it's a polynomial that is an element of the ring such that x squared plus 1 divides P. So that's an ideal, providing throughout we're using the standard definitions of addition and multiplication for polynomials. What's an example of P? Examples here, just P could be 5 on 2x plus 3 pi times x squared plus 1. If you expanded all that out, you'd get a polynomial with real coefficients, and it's certainly divisible by x squared plus 1. Another one is P equals, well, 0, because 0 is just 0 times x squared plus 1. So 0 is definitely in. You get the idea. Just take any polynomial you want and multiply it by x squared plus 1, and that'll be in the ideal. Okay, so the point is that that's an ideal. And then finally, I'm going to do, I'll do final example. Let's do this one. Let's call R equals the continuous functions from the reals to the reals. So you might like to think of this as being anything that goes from the reals to the reals, you know, I don't know, y equals x cubed or something like that. Okay, and what's the ideal? Well, it'll be the functions that are in R, in the ring, and, or if we want, we could actually just mention the ring here. Such that f1 equals 0. So these are the functions that go through to the point 1. Okay, so that's the 4 examples I wanted to show you, 3 of which are ideals and 1 isn't. I hope that's helped. Comment below if you've got any questions on this or any part of mathematics, or drop me an email, coronahelpmathematics@gmail.com.